We're coming up live. Let's pop out this chat and get ourselves set up. And let's also share this out to the world, shall we? Good morning, Stacking. There we are. Okay. Unsafe Rust today. That, send it out. Also, tweet. Perfect, done. And you've proven the chat is working for me today, so I don't even have to keep it loaded up on my my phone for a while. All right, so where are we today? We're on Unsafe Rust. We're on chapter 19, 19, section 1. And this looks like it's going to be a long chapter. You strive to please. Well, thank you very much. I strive to please as well. Okay, so let's just get on started here. So, Unsafe Rust. All the code we've discussed so far has been Rust's memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside it that doesn't enforce these memory safety guarantees. It's called Unsafe Rust and works just like regular Rust, but gives us extra superpowers. Unsafe Rust exists because, by nature, this chapter can't be any worse than yesterday, I hope. I hope so too. By nature, static analysis is conservative. When the compiler tries to determine whether or not code upholds the guarantees, it's better for it to reject some valid programs rather than accepting some invalid programs. Although the code might be okay, as far as Rust is able to tell, it's not. In these cases, we can use unsafe code to tell the compiler, "Trust me, I know what I'm doing." The downside is that we use it at our own risk. If we use unsafe code incorrectly, problems due to memory unsafety, such as null pointer dereferencing, can occur. Another reason Rust has an unsafe alter ego is that the underlying computer hardware is inherently unsafe. If Rust didn't let us do unsafe operations, we couldn't do certain tasks. Rust needs to allow us to do low-level systems programming, such as directly interacting with the operating system or even writing our own operating system. Working with low-level systems programming is one of the goals of the language. Let's explore what we can do with unsafe Rust and how to do it. Miguel, good morning. First stream of the week without severe headache. Well, I'm glad that you don't have a headache this morning. Or morning for me. So after the whole Actix web issue, we know the Rust community really doesn't want unsafe used in code. Yeah, that was the big thing. So if you're listening to this and you don't know what this was, Actix web is a web server written in Rust, and apparently all of the unsafe Rust code that's used, Rust does something clever where you can see it all together, like in one file, essentially, like where it's all being defined and used. And people found over 100 uses of unsafe. They went in, rewrote it, and got it down to 15 uses. So it's possible that they began writing Actix web before unsafe. Like there were certain things that Rust did to like remove that. But yeah, it shows that that people in the Rust community are actively looking for ways to not use unsafe, which is really awesome. That's kind of what we want to get to. Unsafe superpowers. To switch to Unsafe Rust, we use the unsafe keyword and then start a new block that holds the unsafe code. We can take 4 actions in Unsafe Rust, which we call unsafe superpowers, that we can't in Safe Rust. Those superpowers include the ability to dereference a raw pointer, call an unsafe function or method, access or modify a mutable static variable, implement an unsafe trait. It's important to understand that unsafe doesn't turn off the borrow checker or disable any other of Rust safety checks. If you use a reference in unsafe code, it will still be checked. The unsafe keyword only gives us access to these 4 features that are not checked by the compiler for memory safety. We still get some degree of safety inside of an unsafe block. In addition, unsafe does not mean the code inside the block is necessarily dangerous, or that it will definitely have memory safety problems. The intent is that as the programmer, we'll ensure the code inside an unsafe block will access memory in a valid way. People are fallible, and mistakes will happen, but by requiring these 4 unsafe operations to be inside blocks annotated with unsafe, we'll know that any errors related to memory safety must be within an unsafe block. Keep unsafe blocks small. You'll be thankful later when you investigate memory bugs. So like the biggest thing is because these are telling the compiler, but you're also telling your fellow programmers who are reading the code later, this code contains like potentially where bugs will be, and maybe where to look first. To isolate unsafe code as much as possible, it's best to enclose unsafe code with a safe abstraction and provide a safe API, which we'll discuss later in a chapter when we examine unsafe functions and methods. Part of the standard library are implemented as safe abstraction over unsafe code that has been audited. Wrapping unsafe code in a safe abstraction prevents uses of unsafe from leaking out into all the places that you or your users might want to use the functionality implemented with unsafe code, because using a safe abstraction is safe. Let's look at each of the 4 unsafe superpowers in turn. We'll also look at some abstractions that provide a safe interface to unsafe code. If I remember correctly, the problem was they used unsafe in the request header, which means they could send UTF-8, and that's not parsed correctly using unsafe. I don't actually remember, like I didn't look at the specifics about like what was in there, just like the numbers of 100 down to 15. I think it may have been things like, oh, this isn't working, let's just use unsafe, it'll make it work then. More than we have to absolutely use unsafe, there is literally no other choice. But that's a problem that we humans have sometimes, is that it's easy for us to make mistakes, which is why having more eyes on it, which is what happened, is such a good idea. Dereferencing a raw pointer. In Chapter 4, in the Dangling References section, we mentioned that the compiler ensures references are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to references. As with references, raw pointers can be immutable or mutable and are written as const t and mut t respectively. The asterisk isn't the dereference operator, it's part of the type name. In a context of raw pointers, immutable means that the pointer can't be directly assigned to after being dereferenced. Different from references and smart pointers, keep in mind that raw pointers are allowed to ignore the borrowing rules by having both immutable and mutable pointers, or multiple mutable pointers to the same location. Aren't guaranteed to point to valid memory. Are allowed to be null. So wait, does that mean that there is such a thing as null in Unsafe Rust? Don't implement any automatic cleanup. By opting out of having Rust enforce these guarantees, we can make the trade-off of giving up guaranteed safety to gain performance, or the ability to interface with another language or hardware where Rust guarantees don't apply. Listing 19.1 shows how to create an immutable and mutable raw pointers from references. So let mut num equals 5, let r1 equals, so a reference to num as const, interesting, as a reference to const, or is this dereferenced? I32, let r2 equals reference to mut, num as dereference mut, I32. Note that we don't include the unsafe keyword in this code. We can create raw pointers in safe code. We just can't dereference raw pointers outside an unsafe block, as you'll see in a bit. We've created raw pointers by using as to cast an immutable and a mutable reference onto their corresponding raw pointer types. Because we created them directly from references guaranteed to be valid, we know these particular raw pointers are valid, but we can't make that assumption about just any raw pointer. Next, we'll create a raw pointer whose validity we can't be so certain of. Listing 19.2 shows how to create a raw pointer to an arbitrary location in memory. Trying to use arbitrary memory is undefined. There might be data at that address, or there might not. The compiler might optimize the code, there is no memory access, or the program might error with a segmentation fault. Usually there is no good reason to write code like this, but it is possible. Oh, this is fun. Let address equals and then an actual location to memory. Let r equals address as const I32. Interesting. So we can try it and see what happens. That might be fun. I'm getting the idea that maybe it's not set up and won't work until we start using the real unsafe blocks. But apparently we can set up those things. So cd documents projects. We're on chapter 19. Cargo new, and what are we making? It's unsafe. Word unsafe. Okay, so unsafe. And then I want to code here. So it sounds like it's basically let for this one we can let address equals, we could just copy this in. I don't think, my guess is this won't compile. Unused variable r, well, okay. What if I then try to print line? It doesn't implement format display. We could try debug mode. Okay. So let address equals just a completely random place and address. Let r equals, and this probably doesn't exist in memory, but we'll find out. Let r equals address as const I32. So basically we're converting, and it's dereferencing. So whatever is in memory, dereferenced out, that we get the value in there. They're going to try to print what r is. Which in this case just happens to be 0x1, 2, 3, 4, 5. Recall that we can create raw pointers in safe code, but we can't dereference raw pointers and read the data being pointed to. In listing 19.3, we use the dereference operator on a raw pointer that requires an unsafe block. So basically, if we do this in unsafe, I wonder if it's going to be any different. So I guess it would be here, right? Go to home, tab that in. Okay, so let's try this. The chance of actually hitting memory the program had access to would be pretty likely. Yeah, I mean, definitely. Unsafe. Unnecessary unsafe block. That's actually nice for it to tell us that we don't really need unsafe there. And let's go on to the next examples here, which is, so let mute num equals 5, let r1 equals reference to num as, and then dereference to the base pointer const i32. Let r2 equals mutable num as mute i32. So this is going to be similar, but without like raw memory locations. This is us saying, okay, we want to have both a immutable and mutable pointer towards this num. So if we run this, r1 is 5, r2 is 5. If we don't have this r unsafe, it probably will yell at us quite a bit, saying dereference of raw pointer requires unsafe function or block. So it actually tells us we need unsafe if we're going to do this. That's actually really nice. Now with this one, can I also, like up here, I bet I can't, can I say r2 plus equals 3? And I probably can't do that. I probably have to dereference it here. Ooh. To type mute i32, if I dereference it, it's now going to say requires unsafe. So if I move this down here, that wasn't what I wanted. Okay. Now I can. Let's see if both R1 and R2 have been changed. Yeah, they have. So after running that +3, R1 is 8, R2 is 8. So it is exactly the problem that Rust like prevents us from doing, which is we're able to affect a place in memory, but we can only do this in unsafe. Creating a pointer does no harm. It's only when we try to access the value that it points at, that we might end up dealing with an invalid value. Note also that in listing 19.1 and 19.3, we create const i32 and mute i32 raw pointers that both pointed to the same memory location where num is stored. If we instead tried to create an immutable and mutable reference to num, the code would not have compiled because Rust ownership rules don't allow a mutable reference at the same time as any immutable references. With raw pointers, we can create a mutable pointer and an immutable pointer to the same location, and change data through the mutable pointer, potentially creating a data race. Be careful. With all of these dangers, why would we ever want to use raw pointers? One major use case is when interfacing with C code, as you'll see in the next section, calling an unsafe function or method. Another case is when building up safe abstractions that the borrow checker doesn't understand. We'll introduce unsafe functions and then look at an example of a safe abstraction that uses unsafe code. Calling an unsafe function or method. The second type of operation that requires an unsafe block is calls to unsafe functions. Unsafe functions and methods look exactly like regular functions and methods, but they have an extra unsafe before the rest of the definition. The unsafe keyword in this context indicates the function has requirements we need to uphold when we call this function, because Rust can't guarantee we've met these requirements. By calling an unsafe function with an unsafe block, we're saying that we've read this function's documentation and take responsibility for upholding the function's contracts. Here's an unsafe function named dangerous that doesn't do anything in its body. Well, that's the next thing, is that, of course, could the documentation be wrong, and then we run into problems where it's very, like, it's more dangerous than we thought because we didn't use it properly. So unsafe function dangerous, unsafe dangerous. We must call the dangerous function within a separate unsafe block. If we try to call dangerous without the unsafe block, we'll get an error. So call the unsafe function. That's actually really nice because it means that we only have to have one block of unsafe here, but we could have an entire function where we sort of put the unsafe code. By inserting the unsafe block around our call to dangerous, we're asserting to Rust that we've read the function's documentation, we understand how to use it properly, and we've verified that we're fulfilling the contract of the function. Bodies of unsafe functions are effectively unsafe blocks, so to perform other unsafe operations within an unsafe function, we don't need to add another unsafe block. Creating a safe abstraction over unsafe code. Just because a function contains unsafe code doesn't mean we need to mark the entire function as unsafe. In fact, wrapping unsafe code in a safe function is a common abstraction. As an example, let's study a function from the standard library, split at mute. That requires some unsafe code and explore how we might implement it. This safe method is defined on mutable slices. It takes one slice and makes it two by splitting a slice at the index given as an argument. Listing 19.4 shows how to use split at mute. So let mute v equals vec, so a new vector, let r equals reference to mute, vec, so the entire vector, let ab at equals r.split at mute 3. So we're going to get 2, like 1 and 2, and 4, 5, and 6 as a and b. Assert equal, a is mute 1, 2, 3, 4, 1, 2, 3, and then, oh, okay, so the split doesn't actually remove, it's splitting at index, so 0, 1, 2, 3. We can't implement this function using only safe Rust. An attempt might look something like 19.5, which won't compile. For simplicity, we'll implement split and mute as a function rather than a method, and only for slices i32 values rather than for a generic type t. So function split at mute, we take a slice, so mute i32, and a mid usize, and mute i32. We return a tuple, which is mute i32. Well, it's a reference, a mutable reference to a vector of i32s, and a mutable reference to a vector of i32s. Let length equals slice.length. So we figure out how long the thing is. We have to assert that mid is less than length, otherwise it'll panic. And then we mute slice. So then we're returning this tuple, a reference to mute slice, dot mid, reference to mute slice, mid dot. Okay, yep. Everything until the mid, and then everything after the mid. This function first gets the total length of the slice, then it asserts that the index given as a parameter is within the slice by checking that it is less than or equal to the length. This assertion means that if we pass an index that is greater than the index to split the slice at, the function will panic before it attempts to use that index. Then we return two mutable slices in a tuple, one from the start of the original slice to the mid index, and another from mid to the end of the slice. When we try to compile the code in listing 19.5, we'll get an error. So let's go ahead and try to implement this ourselves too. So split at mute. So split at mute. We're going to take in a slice and a mid. So we're going to take in a slice, which is a this a mutable reference? Yeah, it is a mutable reference of I32s. And we're going to take the mid, which is just a usize. And we're going to return a tuple of, is it just a reference, a mutable reference of I32s. Mutable reference of I32 and a mutable reference of I32. Okay, so far so good. The first thing we want to do is we're taking in this array here. Let's get the length of it so we can make sure that our usize is, you know, inside of it. I'm curious why that won't compile. That looks like legit code to me. It does kind of look like legit code, doesn't it? Well, so we're gonna find out pretty quickly. So let size equals slice.lang. Okay, so they're still complaining about return values. Now, so the next thing here is it's really interesting that they do an assert here. Because assert, I think, will just panic if it's not good. So we'll do an assert that, what is it? This is just turning it into a Boolean. So, oh, it's assert, bang. Oh, I've got that. So it's mid is less than size. Okay. Otherwise, it will obviously panic. I'm not sure how I feel about that. Like, I might want to do this manually, where like I just check that, then I can do a print line and then panic with a custom, or just like actually return a result in a proper one, so that main would handle the errors. But this is perfectly fine here. We'll ignore that. And then we want to return a tuple. So the first item in the tuple is the left-hand side. So we want an array, so a vector of dot dot, so everything until mid. And then we want an array of mid until the end. So we'll save this, and mismatch types, expected mute I32 found array of 1 element. Expected type mute I32 found type standard ops range to usize 1. Interesting. Found array of 1 element. Oh, less than or equal. But that won't really change what this error message is telling us. So thank you, stacking. Expected reference to mute I32 founded. Oh, do I have to give like a reference to it? Mismatch types, expected I32 found struct standard ops range 2. Oh, you know what? It's this slice. I need to do this slice. It's slice dot dot mid. Slice mid dot dot. Mismatch types. Types differ in mutability. Expected type reference to mute I32. Found type just reference to I32. So can I put a mute in here? Cannot borrow slice as mutable more than once at a time. The first mutable borrow occurs here. So I'm borrowing the dereferenced slice right here mutably in order to create this. Then I'm doing it again immediately afterwards right here. Cannot borrow slices mutable more than once at a time. Second mutable borrow occurs here. I think the problem is you can't compile the code because it's expecting the full vector back. Well, I mean, I don't think so, because it's taking in a full a reference to a vector, but it's returning two slices back, but two mutable slices. And it's two mutable slices to the same vector. So if I just wrap this in unsafe, does that make everything happier? No, it does not. Or at least not here. Unnecessarily unsafe block. Okay, so I'll wait until it tells me how to actually do it. But we've run into the same problem that they have. If we want to get the actual real error message here, fuse mutable borrow and then second mutable borrow. So Rust borrow checker can't understand that we're borrowing different parts of the slice. It only knows that we're borrowing from the same slice twice. Borrowing different parts of a slice is fundamentally okay because the two slices are not overlapping. But Rust isn't smart enough to know this. When we know code is okay, but Rust doesn't, it's time to reach for unsafe code. Listing 19.6 shows how to use an unsafe block, a raw pointer, and some calls to unsafe functions to make the implementation of split at mute work. Yeah, we all had a brain fart. The problem is you need two mutes. Yeah, yep, two mutable refs. Yep. Okay, so use standard slice. So function split at mute, takes in slice mute, i32, mid, size. So exactly the same contract here. Let length equals slice.length. Let pointer equals slice. So this is not any different, but let pointer equals slice as mutable pointer. And so we're getting at from standard slice. So they're going to give us a mutable pointer to slice. Interesting. Okay, so let's try that. So standard slice. The rules of a programmer, we forget everything, then you just hear screams across the office of how stupid they are. Yeah, what is it? Like sometimes we're brilliant and sometimes we're the stupidest creatures on the planet. I mean, it happens. But part of it is like just getting used to it, and then the more we get used to like the syntax and everything else, the better we get. All right, so we have standard slice. We have let size equals size at length, but we also need this pointer. So let pointer equals, it's going to be slice. Now this seems silly. They have standard slice here, and then slice coming in here. Does that work? That's the same word. Slice as mutable pointer. This feels odd. So as UTR. Like, I can't imagine this working, but I mean, so far it seems okay with it. So we have our pointer, we assert, we do our normal assert, then we have our unsafe block, and we want to slice from raw parts, mutable, pointer to mid. So basically, this is these are unsafe code that we have to call with unsafe to call these these methods that are provided to us from standard slice. So slice from raw parts, mute, pointer, mid. With the namespace? No, because like when we do standard slice, this is the namespace now that we brought out. Otherwise here we'd have to do standard : slice as mutable pointer, which might be what the best thing to do is, or just rename this to not be slice. But I'm gonna do what the book says right now, just to sort of see what the heck they're talking about. So first of all, we have to have, well, let's not use unsafe right now. Let's start over again with this, which is slice from raw parts mutable. So slice from, notice like my editor here isn't able to give me like what's going on. So it's from raw parts mute. Raw parts mute. And we're gonna give it the pointer and the mid. So pointer and the midpoint. So what's interesting here, this is still part of this slice though. Slice from raw parts mute. Okay, and then pointer offset, mid s. Okay, so this is interesting. Slice from raw parts mute. Okay, so let's start there for this one. Slice from raw parts mute. But then inside of here, the pointer, so it's gonna be pointer.offset. So pointer dot offset, and then this itself takes mid as I size, so we have to change mid to an I size. So mid as I size, and then length minus mid to get that middle point. Which is size minus mid. Call to unsafe function requires unsafe function or block. So I think it's because from raw parts mute is a unsafe, like has been defined as an unsafe function. Ooh, they have a so function core slice from raw parts mute, public unsafe function from raw parts. Performs the same functionality as from raw parts, except that a mutable slice is returned. This function is unsafe for the same reasons as from raw parts, as well as not being able to provide a non-aliasing guarantee of the returned mutable slice. Data must be non-null and aligned even for zero-length slices, as with from raw parts. You're gonna check out C Lion. Isn't C Lion, is that the WebStorm people? So call in unsafe code for this. JetBrains, right. And then of course we're not calling it. So inside of here, we don't need you anymore. Well, actually, you are nice to have. Let's now call, so let my vec, or I'll call it numbers. So numbers equals vec of 1, 2, 3, 4, 5, 6, 7. Then we say let, we can destructure here, so it's going to be A and B equals, we're going to call split at mute, and we're going to call the slice, so it's I guess it's just numbers, and the midpoint, let's do like 3. And then we can print line A, B. All right, let's see what they say. Is this? No, it's not. Okay, mismatch types expected. Mutable reference to I32 found struct vector vector. Okay, so I need to give this a mutable slice. So mutable reference of a numbers. Doesn't implement standard format display, so maybe I can do. Cannot borrow immutable local variable numbers as mutably. Okay, so this needs to be mute. All right, so no errors showing up here. Let's try it out. So yeah, this ended up working out exactly as expected. Recall from the slice type section in chapter 4 that slices are a pointer to some data and a length of a slice. We use the length method to get the length of slice and the as_mute pointer method to access the raw pointer of a slice. In this case, because we have a mutable slice to I32 values, as_mute pointer returns a raw pointer with the type dereference mute I32, which we've stored in the variable pointer. We keep the assertion that the mid index is within the slice. Then we get to the unsafe code. The slice from raw parts mute function takes a raw pointer and a length and creates a slice. We use this function to create a slice that starts from pointer and is mid items long. Then we call the offset method on pointer with mid as an argument to get a raw pointer that starts at mid. And we create a slice using that pointer and the remaining number of items after mid as the length. The function slice from raw parts mute is unsafe because it takes a raw pointer and must trust that this pointer is valid. The offset method on raw pointers is also unsafe because it must trust that the offset location is also a valid pointer. Therefore, we had to put an unsafe block around our calls to slice from raw parts mute and offset so we can call them. By looking at the code and by adding the assertion that mid must be less than or equal to length, we can tell that all the raw pointers used within the unsafe block will be valid pointers to data within slice. This is an acceptable and appropriate use of unsafe. So, if I didn't have this check, and I asked it to get not a number that was inside, but like, okay, so 0, 1, 2, 3, 4, 5, 6. If I asked it to like 10, which is way far outside of here, then what will happen? Thread main panicked at a tap to subtract with overflow. Okay, so it didn't do anything absolutely crazy, but it did crash. Note that we don't need to mark the resulting split at mute functions as unsafe, and we can call this function from Safe Rust. We've created a safe abstraction to the unsafe code with an implementation of the function that uses unsafe code in a safe way, because it creates only valid pointers from the data this function has access to. In contrast, the use of slice from raw parts mute in listing 19.7 would likely crash when the slice is used. This code takes an arbitrary memory location and creates a slice 10,000 items long. So just our arbitrary memory location, let r equals address, I32, let slice equals unsafe, slice from our parts, r, which is this address, and 10,000. We don't own the memory at this arbitrary location, and there is no guarantee that the slice this code creates contains valid I32 values. Attempting to use slice as though it's valid slice results in undefined behavior. Well, what happens if I run this? I'm actually kind of curious. So if I put this in here, hit save. Unused variable slice, that's fine. Let's not worry about that. Oh, we're still getting a panic at here. So it runs, and so slice equals unsafe slice from a part. And I now print line slice. Let's see what we get. So we get a segmentation fault, core dumped, cargo run. What's really interesting here is like, so we get this interesting different look. Is this a PID, or I'm not sure exactly what that number is. The UB should be the address, could contain them values or not. Yeah, exactly. So we have no idea what's going on here. 1 in a billion words, it might work, so make it a UB. Yeah, 1 in a billion runs is too long. But like, it's that part where it's letting us run it and compile it, and then it crashes and segment faults. So I mean, that's not cool. I'm gonna go ahead and remove this, and we're not gonna write code like that. We don't own the memory at this arbitrary location. Oh, undefined behavior. Okay. Using extern functions to call external code. Sometimes, is it undefined behavior? Is that UB? I think that's what you meant, right? Stacking. Using extern functions to call external code. Sometimes your Rust code, actually, how much? We might be able to get through this, but we also have a bunch of this other stuff here. So I'm actually thinking I might end up not doing this, because we're probably gonna play around. We might be playing around with this code here, and it's 7:51. So I think what I'm gonna end up doing is just end up moving to start closing the stream down now, so that way we can later like come through this, and then we'll have the rest of this to do. We got halfway through it. I think that's pretty good. Let's begin by closing you down, all in. So playing with unsafe. Undefined behavior is you can't say with 100% certainty that the code will run the same every time. And the problem with undefined behavior is that if you really make it wrong, not only will like one of the possibilities would be crashing, one of the possibilities is actually accessing valid memory that you really shouldn't be accessing. Majority of the time, most people don't even know they have a UB. I mean, that's probably true. It's like nobody well, I mean, I would say it's definitely true, right? If we know we're writing undefined behavior that might crash, we're going to not do that. But if we think we're okay, then we're gonna blissfully, deploy this code, even if it's not cool. The worst ones are when you have a pointer to memory, and it ends up being a valid memory location, and then you're able to actually get little fragments of data from it. And it's really bad if that fragment happens to be like a password or a username or some other data that can be used by a hacker, and they're going to be using that code to really try to infiltrate, get data from your systems, then infiltrate it. Okay, so halfway through Unsafe Rust. Okay, so we're halfway through Unsafe Rust. Before we push this up to GitHub. So next week, Monday through Wednesday, I'm going to be on traveling to, so I won't be able to, I won't be here to be able to do my my normal streams in the morning, but I'll be back on Thursday morning, and then we'll go ahead and continue this off. Let's see, we're almost through with this book. Specifically, we're almost through with the major parts of the book. Chapter 20 is going to be building a web server from scratch, which is going to be really fun. And then after that, it's going to be building out some projects. I already have some in mind for what to do, so we'll be able to jump into that right away. Darn, how will I slack for the next 3 days at work? I don't know. Make some stuff in Rust. Just for the 1 hour, or we can go watch some of the older streams, and I don't know. We'll figure. I'm sure you can figure it out. Okay, so with that, it is Friday, so I want to try my elongated exit message, which is I'm going to come and find my GitHub. You've been blowing up the old streams for last week. Awesome. I hope that they're good, and you're getting stuff from them. I guess you can catch up completely. All right, so I have recently been doing you've got plenty of ones to go through. I'm on 60 something now. Okay, so I'm sharing out the Learning Rust repo that I've created here. This is where all the code that I've been going through the book is, and I've also got a wiki here of, as I've been programming, I've been adding things into here with locations to where it is in the official documentation. That's specifically so I could add specific words that are searchable for things that I haven't really memorized yet. And I would love, if it ends up being helpful, please let me know. Also, if you have any, we have issues here that we've been using as information. If anything that has been wrong in the videos, or that you want to add your 2 cents to it, please feel free to submit an issue, and I'll read it out on the stream. Besides that, I am archiving all these videos over to YouTube, and I have links to all the places in the stream description and the video descriptions on YouTube itself. And then finally, I have my Twitter account that I've been posting when I'm going live right then too. It's rare that I do a unscheduled stream, but when I do, I also put that on Twitter right about that time. And of course, you can always follow me here on Twitch and follow me on YouTube to get the actual push notifications when I go live, so you don't have to rely upon me remembering to do that. And it's automation, right? People make mistakes, and automations don't as much. 40 hours to go. See, that's a full week. I'll be back by the time you're done. Okay, so with that, I am gonna go get ready for the rest of my day. I hope that you have a great rest of your Friday and a great weekend, and I'll see you all on Thursday next week. Bye.